All right, so just again to get our intro back in here. We have two products here subtracted, and we get those products by multiplying in diagonals. The diagonals do make an x. We multiply in diagonals, we get the 1 times the 1, the 2 times the 4. And we're really trying to learn about finding the determinant using spatial, using where things fit in relation to the other values. So, but this determinant is going to help us solve systems of equations by the end of the week. The first step in finding the inverse of a matrix A is using the determinant. So we're working towards tomorrow. We're going to deal with the inverses, but today we're just dealing with determinants. Help us find our inverse. Here's the notation. It looks like the absolute value notation. And we can only find the determinant for a square matrix. So if we got a 3 by 2, we have a 2 by 3, a 5 by 4. We can't do that. It has to be 2 by 2, 3 by 3, 4 by 4, and so on. It just gets a little confusing when it gets really large, but as long as it's a square matrix, we're okay. All right. So we know that if A is equal to A, B, C, D, then our determinant of A is going to be A times D and B times C. It's just going to be, again, just multiplying in diagonals. Okay. So unfortunately, I didn't erase this. That's okay. This is not a very difficult topic. To just find the determinant is very straightforward. It's a pattern. When we get to 3 by 3, it gets a little trickier, but I don't want to hold us up here. We know we're going to end up with two products, and they're going to be subtracted. So from this matrix, what values are going to go in here? 3, 4. That's here. 3 and 4, and then 1, negative 2. You just have to be careful here. This is 12 plus 2, right? 14. Just watch your signs. Pretty straightforward. So the determinant of this matrix A is 14. And I would write it like that. So the second one, I almost feel like it's going to be redundant to even check you again, but all right, what do we get with this? This product is 0 minus 4, so we get the determinant of B is equal to negative 4. I mean, for 2 by 2, just finding the determinant, what do you guys think? Thumbs up, sideways, down for this? Feels good? Okay. Now, just notice if you're really devoted to trying to memorize. If you're really into memorizing things, I want you to try to learn this in a different way. Okay, so let me erase some of these colors that are left here. All right, first off, if we have a 3 by 3, it gets a little bit more complicated, just a little bit. If we have a 3 by 3, here's matrix A. We're going to take the determinant of matrix A. We're going to find that. And what we first look at is this top row. I want you to, maybe I'll do some side notes here, just kind of like arrows. This top row, these are our scalars. When we find the determinant for a 3 by 3, we have to break it up a little bit differently. Okay? Now the process is called, actually it's my student teacher calls it the cross tactic. We'll keep it there because it's in the notes. But the cross tactic basically looks at, we're going to end up with a positive, a negative, a positive. And you keep on growing it negative, positive, between each of these determinants. A starts with positive. So I look here, it's A. And what I'm going to do here is, I'm going to go ahead and use my cross tactic to find out what determinant is multiplied by A. So I'm using the top row to know what my scalars are. Those go in front of each determinant. And then when I cross out the row in the column, using the cross tactic, the leftover in the matrix is what's going to be the determinant we have to find. So you see, when I have A and the determinant of E, F, H, I, that comes from doing the cross tactic to get what's left over in the matrix goes right here. And we're going to find the determinant of that, work through it. Gene?
So I'm just wondering, like, what know, when you add matrices, like, you know, you're defining them. You
Yeah.
try to move one away from the other. Like,
Good.
what?
Like, what's the use of it?
Yeah.
Perfect question. So by the end of the week, we're going to solve systems of equations where we have, you know, you could have, watch, if you have this, let's go this x. That's 2y minus 3z is equal to 8. And then you have 4x minus y plus z is equal to negative 17. You know, this is a very complicated problem because you'd have to solve this by elimination. You'd have to multiply them all so you get one of the terms where you can be able to cancel them all out. Then you'd end up with 2 terms you'd have to deal with and do it over and over that process. Now, solving systems of equations like so. Actually, these would be gone. That's better. Solving systems of equations like this, okay, involves the step of using the determinant when you're doing this using matrices. So if we want to solve this using the matrices, we need to find the determinant to the next step tomorrow, which is finding the inverse. So once you know the determinant, the inverse, then you can go about actually solving these. You need those 3 tools to be able to solve it.
So by itself, it's not really used for anything.
No, it doesn't have a specific use other than it's the step is to find the inverse. Find the inverse. So it's kind of like a baby step, but this right here, this pattern is complicated enough I want to spend a day on it. Okay. What happens when if I'm looking for now my B scalar and what's involved in that, watch what happens. Take away the red line. And I'm going to do the cross tactic with B. You see how I found what's left over and what goes in this determinant? It's just what's left over in the matrix, right? Use the cross tactic. It's always going to have what's left over in the matrix. D, F, G, I goes right here. Next with C, we're going to go and look at that, and you can see where we're going with this. You can see now. Cross tactic, what's left over in that determinant? D, E, G, H. Okay. So don't memorize this. From this step, we know how to do the 2x2 determinant. We would just do that like we did over here, and then whatever you get for that, you'd multiply it by the scalar of A. You multiply by A. Okay? So you do that for each of them. The key step is here, remember, pattern is plus, minus, plus, minus. When we get over to this example problem, this is going to be where we work it all the way through. So let's look at this example problem. All right, so first off, let's go ahead and first set up our scalars and the room for the determinants. Room for the determinants. So let's see. What are my scalars going to be? For 1, right? My scalars are 6, 1, and 1. So I need to go positive 6 times some determinant. And then what's next? Right. Minus 1 and some determinant. Next? Plus 1. Plus 1 and a determinant. See, these are our scalars. They're set up right here. And then we're just going to use the cross tactic. I want you to go ahead and use the cross tactic to find what is going to be, what's going to fit in this first determinant. So go ahead and use the cross tactic using this. And I just realized I can use this. All right, double check your neighbor. Double check your neighbor what they think. What goes in that determinant? A question for the group, or you know?
I don't know.
Okay. You have 4x4, determinants in that case. 3x3 like this, but determinant is going to be 2x2. So it finishes it.
So basically, 6 times this,
this, you would have to do that again. So, I mean, just think of it as like a 2 by 2. Oh, I see. I would actually find my answer for this. Answer. Okay. Oh, yeah, do the determinant first, then multiply by 6.
Yeah.
All right, that took a minute. Sorry to get a little distracted here, but let's use these pieces of paper. So I'm going to do the cross tactic for our first scalar, which is 6. Using the cross tactic, I'm going to go ahead and do what? Cover up those. So what goes in that determinant? All right, -2, 5, 8, 7. Remember that this scalar really works just as if I had a polynomial and I had, -2 plus 5 plus 8. Now, you could do this and you could say, well, I want to really distribute it first. Or you can combine what's on the inside of the parentheses, thinking PEMDAS, then just multiply by 6. So I say let's not distribute the 6 into this, which scalar would just be multiplying this by 6, 6, 6, 6. If you do that, you're going to end up just having larger numbers, and you're going to end up subtracting them anyway and getting the same value at the end. So what I'm just proposing is we're going to work this one out and then multiply by 6. How about for 1 or -1 we get, or it was 1 actually. We end up with this right here. Where's my 1,000 magnets? So we end up with 4, 5, 2, 7. Somebody help me out. What's the last one we have?
4, -2, 2, 8.
2, 8? Like that. Okay. So I'm going to work on this first. I'm going to go ahead and make it. You know, a good question was brought up. What is the matrix we're starting with up here? This matrix is a what? 3 by 3. So what do all our determinant matrices end up being? 2 by 2. Just dropping things day? All right, so if we had a 4 by 4, what kind of determinant are we going to end up with? 3 by 3, and then we'd have to do this process again to be able to find it. So you can see that if you had a 10 by 10, you'd have to work really hard to whittle it all the way down to get the actual value. Okay, to find the actual determinant. So it does get tricky, but we're not going to do 10 by 10s just yet. In fact, you won't see anything more than a 3 by 3. That's the standard says go to 3 by 3. So I look here and we have 6 times. Right? You see how I'm setting that up? It ends up being -2 and 7, 8 and 5. We can work that out. That's no problem. -1 times 4 times 7. 5 times 7. Plus 1 times 4 times 8 minus -2 times 2. Doesn't matter when I'm multiplying in diagonals if I multiply this times this or that times this. It doesn't matter which one I multiply because 2 times 3 and 3 times 2, same thing.
And the middle, term, isn't it 5 times 2 instead of 5 times 7?
Yeah. Okay, thanks for the catch. All right, everybody, see I just changed this. I accidentally wrote 7. It's 2. But you see from here on out, we can do this. We can solve each, we can multiply each, we can subtract or add each. So let's go ahead and do that. I'll just say 6 times. This is -14. This is 40. Negative. Minus. Hey, your seat's right there. So we get -54 times 6. Here we get 28 minus 10 There's a minus out here as well, but this is end up being 18 times a negative 1, negative 18. 32, negative 4. There's another minus there, so that ends up adding to 36. It's plus 36, so plus 36. You see, you get there quick. 324 negative minus, well, we could see this is going to add to give us 18. What's it?
306.
Negative 306. Now, the only thing actually that's really kind of a challenge to this is, I believe it's the cross tactic. You have to do that. What's another crux? Anybody else have a candy crux? Candy. Yeah, Bella.
Just dealing with all the numbers and all the parentheses.
Parentheses,
and
numbers.
Understanding which means which.
Which means which. Okay. Perfect. Thank you. So, any other candy cruxes out there? Ooh, you get to watch my video, I think. Yeah. Any other candy cruxes? Yeah, Sonia?
You might confuse the lines for absolute value.
Yes, that's true. But context. Within matrices, we use these, and actually I'll look it up. There's likely a different name for these brackets. I'm not sure right now. I'll look. All right. Anything else, Candy Crux? All right. You can get started on the homework. I'm going to put it up right here. It's on Edmodo if you want to look already. And that'll be it for today.